Chapter 11, Part 4, Epoxides and Crown Ethers. So we're going to start with just the synthesis of epoxides and also what is an epoxide, just all at once. So an epoxide is a three-membered ring where one of the members is an oxygen. So this is a cyclic ether. The IUPAC name for this functional group is oxirane. The common name for this particular epoxide is ethylene oxide. And I told you when I introduced the naming of cyclic ethers earlier that epoxides are named based off of the alkene that it was made from. So ethylene oxide is made from ethylene, and notice it also uses the common name because this is part of the common name. And typically reacting with a peroxybenzoic acid, such as metachloroperoxybenzoic acid, which is also shorthanded as MCPBA pretty regularly. And that just creates an epoxide on the two carbons that are part of the alkene. Also remember that when you create a three-membered ring from an alkene like this, it is going to be cis, right? They're going to be on the same side. So this compound coming from propylene and reacting with MCPBA is going to be called propylene oxide. Now, something that you do see in practice problems, not just in our homework, but online, also in other textbooks and things like that, is that MCPBA is not the only peroxycarboxylic acid that can do this. So anytime that you see the peroxycarboxylic acid group, which is specifically this, right? It's a carboxylic acid that has one extra oxygen in there. And it's reacting with an alkene, it's going to do this. It's going to make an epoxide. That's what this functional group does with alkenes. So we're not just looking for MCPBA, we're looking for any peroxycarboxylic acid. It's just MCPBA is really, really common. And again, this is a syn addition, and it's pretty simple to do that with a very straightforward alkene. If you get your alkene a little more interesting, you're going to end up with a slightly more interesting epoxide. And just make sure that you stay on top of that stereochemistry. So you can put these both up or you can put them both down. So let's talk about the stereochemistry of epoxidation in more detail. Because there is a difference in stereochemistry based on whether your starting alkene is trans or cis. And I think the easiest way to picture this is actually, even though we draw alkenes flat because they are trigonal planar, you need to look at it kind of from the front. So imagine that you're looking at this compound, maybe holding it flat in your hand, and all four of these carbon atoms are in the same plane. If you're looking at it from the front, this methyl group is coming towards you, and this one's going away from you. So that's how we're drawing them here, coming towards and going away. And then I can draw this, imagine it as the epoxidation happening from the top, because it is a syn addition. It happens all on one face, and that would give us this epoxide. Now, if the epoxidation happens on the bottom face of my molecule with the way that I'm currently holding it, it's going to give us the enantiomer, which would look like this. If you want to see how that looks like if we keep the alkene in the same place, in this case it was made and then flipped over. I think the easiest way to explain this is to draw it. If we keep that one methyl group coming forward and that other one going back, and we made the epoxide on the bottom, it would look like this. So then that hydrogen would be going back, and this hydrogen would be coming forward. So this is the kind of direct comparison to this. Epoxidation from the top face, epoxidation from the relative bottom face. These are enantiomers of each other. If you took this and plopped it directly underneath it, it would look like a mirror image or a reflection in water. If you took that molecule I had drawn in blue and flipped it over so that the epoxide was up, it would look like this. Now, if the molecule is symmetric and cis, then you're going to end up with one meso compound because the methyl groups are coming towards you. And so even if you were to draw it with the methyl groups going away from you, and the epoxidation, you could draw it up, you could draw it down, whatever. These would be the same compound, just rotating in a plane. So imagine taking this compound and rotating it like this. So imagine like you have it on a stick, like an axis, and you're rotating around that axis. It would just look like this compound. So even trying to create its mirror image just gives you the same compound right back. And you can see that also if you imagine your mirror plane this way and just try to draw the exact mirror of the compound. You get the same thing right back. So this is a meso compound. Now again, this only works if these two substituents are identical and the molecule has a plane of symmetry. If the molecule does not have a plane of symmetry, then we have to worry about our stereochemistry a little bit. So if you react with MCPBA and a cis alkene, one of your options is going to be like such. And you can also draw it, you can have the methyl groups, or methyl and ethyl group like this, and the epoxide down. These would actually be mirror images of each other. If you imagine flipping this right side up, it would look like this. So you end up with an enantiomeric pair, just like you do with the trans. But notice that the stereochemistry of these is different. If we had reacted with the trans version of this alkene, we would have to put one of these in dashes in order to make this work. So let's look at reactions of epoxides. We talked earlier about cyclic alkanes and how a cyclopropane ring is under a lot of ring strain. Now when it's cyclopropane, that doesn't really result in anything. It's not really particularly reactive because carbons, hydrocarbons specifically, are not particularly reactive. But if you have an epoxide, now you have something that can act as a good leaving group, and it's also been polarized. And so these carbons have become a little more electrophilic. So now it's susceptible to nucleophilic attack. And depending on the conditions of the nucleophilic attack, your outcome can be a little different and unexpected. So let's look at the acid catalyzed ring opening. First, we're just going to do this with ethylene oxide in both conditions just to talk about the mechanism. And then we'll talk about the regiochemistry involved in this reaction. So the epoxide in acid would get protonated, just like we're seeing in the first step here. And then water would come along and attack one of the carbons, and that's going to break open this bond. These two electrons would end up going on the oxygen. And so what you're doing is, here's your epoxide oxygen, your epoxide carbons, and then you have your water molecule that had attacked, and you deprotonate it. So now you've made a diol. And also, this should really, really remind you of the reaction with bromine, right? We end up using a bridging bromonium ion as an intermediate, and then that was susceptible to attack with bromide. And that ended up being a trans reaction, right? Our outcome was always trans. Same thing here. We're creating a three-membered ring that's going to be in one direction, right? One face of whatever your compound is. And water is going to have to come in and do a backside attack. So you're going to end up with some cool stereochemistry. Now, if you do this in base, it's just a little simpler because you don't have to worry about protonating. You add in a good nucleophile, and it's going to attack and pop it right open, just like an SN2 reaction. And then you're going to want to have a proton source around. Typically, it's the solvent of the reaction. So in this case, it was an alkoxide in alcohol solution. So we can just protonate using the alcohol. And now we have an alcohol on one side and an ether on the other, or whatever your nucleophile might have been. Okay, so let's talk about regioselectivity. This really only matters if you have an asymmetric epoxide. On our previous slide, the epoxide was ethylene oxide and it was symmetrical, so it didn't matter which carbon you attacked. I just picked the one that was closest. But if it's asymmetric, it does matter. So in basic conditions, this is the one that definitely is going to go with your instincts. We know that nucleophiles like to attack the least hindered carbon in an SN2 reaction, right? And this is essentially just an SN2 reaction. So the nucleophile, whatever it is going to attack the least hindered, least substituted carbon and break the ring open until you get to your product here. So our nucleophile attacked the least substituted carbon, and that means that the alcohol ends up left on the most substituted carbon. But if you react an acid, your nucleophile is actually going to attack the most hindered carbon. And this should remind you of the halohydrin formation. When you have a protonated three-membered intermediate like this, or you have a positive charge on it like you did with the bromonium ion, this is going to start to resemble a tertiary carbocation. And that's going to make this carbon more susceptible to attack. So let's take a look at this example. This one looks kind of complicated, but it's really not. You just have to keep track of everything. So notice first of all that the epoxide is a repeating feature in both of the starting material and the product. The difference is that this one is an alkyl chloride, this one is an ether that looks like it was formed by reaction with ethoxide. So simple enough, right? The only caveat here is that we have a carbon-14 labeled atom. And now using a labeled carbon is a really common way of trying to figure out how a mechanism works. And the carbon-14 atom is not moving within the molecule. So we know that the carbon-14 atom starts off as part of the epoxide, and by the end, it is not part of the epoxide. So how does this work? That rules out reaction of ethoxide just directly attacking here and kicking out chlorine. If it were to do that, we would end up with this product, asterisk here, epoxide here. And that's not what we have indicated as our product. So where is the only other electrophilic position? You may also notice that the oxygen of the ethoxy group is attached to the carbon-14 labeled carbon atom. So that's kind of a big hint there as well. But this is going to be an SN2 reaction where the epoxide is the electrophile. And in this case, it's this carbon-14 labeled atom because this is the least substituted carbon, and this is an SN2 reaction. So it's going to attack here, and that's going to cause this ring to break open. So we have an oxygen with a negative charge. We have our carbon-14 labeled atom, and we have our ethoxy group. So now at this point, there is no source of protons. Notice nothing has been indicated. So what must be happening here in order to reform the epoxide and get rid of the chlorine is that the oxygen comes along and kicks out chloride, reforming the epoxide. So let's look at just a couple more reactions. We've seen 1,2 dihydroxylation reactions before in chapter 8 with potassium permanganate and osmium tetroxide. But we can also do this by making an epoxide, and this gives us a different outcome. The potassium permanganate and osmium tetroxide reactions give you a syn 1,2 dihydroxylation outcome. This is a way to do an anti 1,2 dihydroxylation. So if you take your alkene and react with MCPBA, you get an epoxide. From here, you could react with aqueous acid or with hydroxide. Either way would work, and you end up with enantiomers. The kind of tricky thing about this is that if you do this in acid, there's the possibility that since this is highly substituted, that the hydroxyl group will leave without water kicking it out. So you may end up with some of the syn product. it might be safer to do this reaction in hydroxide if the anti-product is what you really have your mind set on, because then you could just know that it's going to directly attack and give you that anti-stereochemistry. Either way, you end up with a pair of enantiomers that have the anti-stereochemistry. Okay, so there's also something else really cool that you can do with epoxides, and that is the formation of a polyether, which is a type of polymer. So if you take an excess of epoxide and react it with a small amount of a nucleophile, it can be a methoxide group and an alkoxide to keep the ether thing going, or it could be something like fluoride. That's just a good nucleophile, can bust this open and get the rest of the reaction going. But when you do this first reaction and you have an excess of epoxide, the resulting alkoxide is still nucleophilic, and so it can continue to react with the epoxide. And after many, many steps, you can end up with a polyether that has an alkoxide terminus. You can add in some sort of proton source. You don't want to add in acid because this, you could end up cleaving your ether like we saw in a previous reaction. But adding in something like methanol or water or maybe a very small amount of acid in a solvent will allow you to protonate the end. Now, last thing we're going to talk about is a cyclic ether. Now, crown ethers are macrocycles, which just mean that they are kind of larger cyclic compounds. Crown ethers specifically are cyclic oligomers of ethylene glycol. You use the term oligomer when they have a more limited number of monomers instead of using the term polymer. Polymer implies something much larger than just a couple repeating units in a circle. So that's why we're using the term oligomer here. And ethylene glycol, again, is this unit, right? So crown ethers are considered a derivative from ethylene glycol. The nomenclature of crown ethers is really simple, and this is something that I do usually put on a test because it should be kind of a freebie. The format is X crown Y, where X is the total number of carbon and oxygen atoms, or rather the total number of atoms that you actually draw within the cyclic structure, and then Y is the total number of oxygen atoms. So, for example, this compound has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 total units or pieces in the cyclic structure. So I would call this 18 crown, and then 1, 2, 3, 4, 5, 6 oxygens. So 18 crown 6. So that's where that name comes from. Kind of a fun little naming scheme as long as you remember how to do it. So count everything that's in the cyclic structure. The only thing that we're not counting are the hydrogens on here. And then say crown, and then write in the number of oxygens. Now what's cool about crown ethers is that they are host molecules, meaning that they can host a guest molecule. Crown ethers, being kind of on the smaller side, tend to mostly interact with cations. So crown ethers can be used to solubilize salts in nonpolar solvents. Because remember, salts are going to be soluble in polar solvents, but if you need to bring it into something that's nonpolar, like an organic, like hydrophobic solvent like hexane or benzene, you could do that by associating your salt with the crown ether so that the crown ether can sequester the cation through ion dipole interactions. Remember, all these oxygens are polar. They all have a partial negative on them, so they're going to be really interested in that cation, and then that frees up your nucleophile. So this is useful in a couple different ways. One, like I already mentioned, you can use these to solubilize ionic compounds in non-polar solvents, because look at how many carbons are on this, right? They're going to be able to be solubilized in polar solvents, and the oxygens will allow them to interact with cations and bring them into the polar solvent. You can also improve the rate of an SN2 reaction by adding in a crown ether to isolate the nucleophile. So for the same reason, not only can you solubilize the salt, but by sequestering the potassium ion here, that frees up fluoride and essentially increases the available amount of fluoride, which will increase the rate of SN2 reactions. Now, when you use crown ethers to bring an ion into a nonpolar solvent, they are called phase transfer catalysts. So you might take an aqueous solution of potassium fluoride, add in crown ether, allow them to associate and get to this point, and then you add in your nonpolar solvent, give it a really good shake, and the potassium and the fluoride will be brought into the nonpolar solvent. So phase transfer just means like between two different phases, nonpolar and polar phases. And that is the end of chapter 11 and also the end of OChem 1.